In this module, we're going to introduce the concept of probability. This is one of the most foundational topics in the study of statistics. Everything we do from here on out will depend on the probability of drawing certain scores or certain sample means from distributions. Research always begins with a question about an entire population. We don't usually just care about the people in our sample. We care about the entire group of people from which the sample was drawn. But our actual research is conducted using samples that were drawn from the population. And we're trying to use those samples and how they behave in response to our treatment or whatever experimental paradigm we've put them through. And we're trying to say something about the larger group, about the population, using that sample. Inferential statistics use sample data to answer questions about the population. But in order to do that, we have to establish the relationship between the samples and the populations. And this relationship is defined in terms of probability. Probability is used to predict what kind of samples are likely to be obtained from a population. Thus, probability establishes a connection between samples and populations. Inferential statistics rely on this connection when they use sample data as the basis for making conclusions about populations. So, to restate that in colloquial terms, here we have a population. This is the group of individuals that we're interested in. This might be like all females attending college. And probability establishes how likely we are to have certain characteristics of samples that are drawn from that population. If you remember back to the first module, we talked about this principle called sampling error. And that was the fact that every time we draw a sample, the characteristics are going to be a little bit different from the population. It's not ever going to be exactly the same mean or percentage as the population mean or percentage was. There's always going to be some sampling error, some difference between the sample and the population. But we can say with relative certainty that when we draw a sample from the population, that the probability of drawing a sample with those particular characteristics is of a certain established percentage, a trustworthy percentage. And I'll talk to you more about that in a minute. But the point here is that when we draw a sample, we know the characteristics that we can that we're likely to get in our sample based on the probability of certain characteristics in the population. And then, when we draw that sample and we compute the mean or standard deviation or percentage or whatever it is we're computing from the sample, and we try to say something back about the population, we're using inferential statistics, which are like probability turned on its head. It's like making some kind of reverse probability statement about the kind of population we can expect to have drawn our sample from based on the characteristics of the sample. Remember, we don't know what the population mean is most of the time. Sometimes we do, but most of the time we're not going to know exactly the characteristics of the population because it's too hard to measure everybody in the population. So instead, we measure something about the sample and we try to make a guess about the kind of characteristics the population is likely to have based on reversed probability, or inferential statistics. So let's take a moment here and define probability. You first have to have several different outcomes possible. And then, the probability of any specific outcome is a fraction or proportion of all the possible outcomes. So the probability of event A occurring is equal to the number of outcomes that were classified as A, whatever we've called A, divided by the total number of possible outcomes. An example of this would be the probability of selecting an ace from a deck of cards is how many aces there are divided by how many total cards there are. We use some specific notation when we're dealing with probability. an italicized P is the symbol for probability, and usually after that, we specify in parentheses that there is some outcome that we're interested in, some event. So the probability of drawing a red ace from a standard deck of playing cards could be symbolized as italicized P with parentheses red ace, as the event we're interested in finding. So the probability of obtaining a red ace would be 2 red aces out of 52 total cards, and we would say that that's equivalent to a proportion of 0.04 or 4%, which is also to say that it's the probability of 4% drawing a red ace. Probabilities and proportions are actually equivalent to each other, a fact that seems trivial now but is going to become important later. Let's take this example here. Imagine you were to draw 1 marble from each jar. The first jar has a probability of drawing a white marble at 0.5, and the second jar has a probability of drawing a white marble at 0.1. If you were to draw it from the first jar, what color do you think the marble would be? Hopefully you said something like, we couldn't know, it's about 50-50, it's an equal chance of getting a black or a white. But what if you were to draw from the second jar? What color do you think the marble would be then? Hopefully you said there's a much higher likelihood that it would be a black marble. It could be a white one, but we're pretty certain that the chances are it's going to be black, because 9 times out of 10, it's going to be black. But trying to predict the sample from the population is actually the opposite of what we want to do with research studies. In other words, what we just did on the last slide was we tried to say, what kind of sample will we get if we know all about the jar? In real life, what we want to do is look at what we have in our hands after drawing from a jar and try to guess the kind of population, the kind of jar that it came from. So we have to reverse the rules of probability and make a guess about the population based on the sample that we drew. So this is kind of what that might look like. If you were blindfolded and drew a sample from one of these 2 jars, but didn't know which one you drew it from, and you looked in your hand thereafter, you might ask, which jar did the sample come from? Now, with 4 black marbles, you could probably safely assume that it came from the majority black jar. Why might you say that? Because most of the marbles in the second jar are black, and most of the marbles in your hand are black. So you could say that the sample in your hand looks more like the population from the second jar than the first jar. Could you have drawn 4 black marbles at random from the first jar? Well, certainly, but it's more likely that it came from the second jar. Probability has a limited range. It spans from 0 to 1. Imagine an extreme example where you have only black marbles in a jar, and the probability of drawing a white marble then would be 0, and the probability of drawing a black marble would be 1, or 100%. Because you have 0 white marbles out of 200 black, or 200 black marbles out of 200 black. So you can see there in the most extreme example, where every case is the same, you have either a 0 or 100% chance of getting the events in your population. Random sampling is a process or procedure that's used to draw samples. It means every item in a population has an equal chance of being selected for the sample. In the case of the jar with marbles, that would mean that every marble had an equal chance of being selected. If you think about it for a minute, it would be difficult to establish a random, an independent random sample from a jar because the marbles at the top of the jar have a higher likelihood of being drawn, unless you committed the person to really dig around and not just pick the marbles from the top of the jar, but really reach in and grab any marble anywhere in the jar. The independent word that we use at the beginning of this clause, that modifier means that the probability of selecting a given item in the population is not dependent on the probability of selecting any other. We generally leave off this word, and we just call it random sampling, even though when we say the phrase random sampling, we mean independent random sampling. In order for our probability to be accurate, and thus for our statistics to be accurate, we have to use independent random sampling. So let's talk for a minute a little bit more detail about what independence means. Consider if you were to draw 2 cards from a deck. On the first draw, the probability of obtaining the Jack of Diamonds is 1 out of 52, because there's only 1 Jack of Diamonds in the deck. If you keep the first card in your hand before you draw the second card, then the probability of obtaining the Jack of Diamonds on your second draw changes. Now it's either 1 out of 51 if on the first draw the card that you got was not the Jack of Diamonds. Then there's still a Jack of Diamonds left to draw, but there's only 51 cards left in the deck to draw from. Or if the first card that you drew was the Jack of Diamonds, then the probability of drawing the Jack of Diamonds on your second draw is 0 because there is no Jack of Diamonds left in the deck. Therefore, this method of sampling, called random sampling without replacement, violates the independent condition. The probability of selecting a given item was dependent on the probability of selecting another. So, an independent random sample requires random sampling with replacement. So whenever you draw a person or a case from the population, you have to put it back in the population and run the risk that you could draw that person or that case in your sample a second time in order to meet the case of independent random sampling. In real life, though, we hardly ever actually collect independent random samples. That is the gold standard. That is the ideal. And in order for our statistics to be 100% trustworthy, we have to achieve that ideal of independent random sampling. All of our inferential statistics, in fact, depend on that. However, we often break assumptions that are underlying our statistics, and this isn't the only one of them that we break. In real life, we have to just do the best we can. We approximate random sampling in all the ways that are within reasonable reach, but sometimes we can't exactly achieve independent random sampling. For instance, if you drew a random sample of 30 students from Central Washington University, you wouldn't want for one of the students to be in your study more than once, because that student would unduly influence the mean, the standard deviation, the percentage of your sample, because that person would basically be double counted in the sample that you drew. So you would like to be able to exclude from your sample somebody who has already participated. I want you to think for a minute about some examples of sampling procedures and think about whether or not they are independent random samples. One example might be, say that you went to the library at the Ellensburg campus of Central Washington University, and you picked random people who were walking by to participate in your sample. Would that be random sampling? Not really, because the people who you've chosen are not equally plausible to be chosen in your sample from all the students at Central Washington University. Some people are more likely to walk by the library than others. For instance, anyone who is an on-campus major is far more likely to be on campus walking by the library than anybody who's an online major. Similarly, you might say that the people walking by the library are more likely to have classes in the buildings that are near the library on campus. And so the people who are in classes far away from the library are less likely to walk by the library and are therefore less likely to be drawn in your sample. So not everybody on campus has an equal opportunity of being chosen if you just stand outside the library and pick people at random. So that's not an independent random sample. However, we often might find that that would be a sampling procedure in a real-life study because we might not have the ability to actually independently draw people from the population. For instance, a true random sample might be to get a list of all the students who attend Central Washington University from the registrar's office, complete with their contact information, and then to reach out to a random sample of them and require them all to participate. By doing that, you would actually have an equal chance of all the people on that registrar being chosen because you might use some kind of random number generator on a computer to pick the people who would be in your study, and you would reach out to them, and they would all be in your study, and that would be random. But we often don't have access to a registrar's list like that because information is confidential. And even if we do have access to a list like that, you can't actually require everybody that you select for your random sample to participate. And so sometimes if somebody declines to participate, all of a sudden your sample is no longer truly random because the one that you chose to be in your sample isn't actually in your sample. Therefore, in real life, we just do the best we can. We try very hard to make truly random samples, but when we don't, we just suspend our disbelief in the validity of our statistics, and we hope for the best. Let's talk now about probability and frequency distributions. We can calculate probability of certain scores from a frequency distribution graph because proportions and probabilities are, like I said before, equivalent. So a particular portion of the graph corresponds to a particular probability in the population. You can see that in this example here. This is a frequency distribution histogram for a population that consists of just 10 scores. I might ask, what's the probability of selecting a score greater than 4? These two shaded cells are 2/10 of the whole distribution. Therefore, the probability of selecting a score greater than 4 in this distribution is 0.2, or 20%. A normal distribution is a common shape that's defined by a particular equation. You don't have to know this equation. This involves some degree of calculus and very sophisticated mathematics. The point is, all normal distributions follow this particular equation, and therefore they all have the same percentages under each portion of the curve. A distribution is normal if and only if it has all those right proportions under each part of the curve, where we use z-scores to identify the sections. So, in the section between the mean and one standard deviation higher than the mean, we see 34% of the scores must fall. Between one standard deviation above the mean and two standard deviations of the mean, 13.59% of the scores will fall. And above two standard deviations, 2.28% of the scores will fall. Because normal distributions are symmetrical, so that the lower side of the distribution matches or mirrors the upper side of the distribution, sections on the left side have the same proportion under the curve as they did on the right side. So here, this also has 34.13%. This also has 13.59%. Because these scores define the sections, the proportions of area apply to any normal distribution, regardless of its mean and standard deviation. As long as it's a normal distribution, these percentages hold true. So the reason why I was able to say in previous modules that about 70% of the scores fall between +1 and -1 standard deviations is because, without fail, by definition, every time you have a normal distribution, 34.13% fall in this area, and 34.13% fall in this area, and if you add those two together, it's 68.26%, or I might say about 70. I also might say that about 95% fall between -2 and +2 standard deviations of the mean. It's not exactly 95%, but about 95% fall somewhere between +2 and -2 standard deviations. Let's go through an example of how this might be used. SAT scores have a mean of 500 and a standard deviation of 100. We might ask, what is the probability of randomly selecting an individual from all the folks who've taken the SAT from the population who has an SAT score greater than 700? In other words, if we marked off this section right here, that was 700, and shaded the tail region, these are the people who have scores greater than 700 on the SAT. The first step in answering this question would be to translate this into a proportion question. Out of all the possible SAT scores, what proportion corresponds to scores greater than 700? We then have to identify the exact position of this 700 score by computing a z-score. If you take the x minus the mean divided by the standard deviation, you will see that the z-score is 2, marked here. We can then recall back to the graph I showed you a couple slides ago and remind ourselves that above a positive score of 2 standard deviations, or a z-score of +2, we see 2.28% of the scores fall in this tail region. So we could also say that 2.28% of people in the distribution, in the population, have scores above 700 on the SAT. Now that's pretty cool, but that graph I just showed you lists only the proportions for a few z-scores, just those around +1, +2, -1, -2. And that is somewhat useful, but it breaks down pretty quickly. A more useful tool is the complete listing of z-scores and proportions in what's called the unit normal table. I've uploaded this to the assignment in Canvas, and I've called it table B.1 zdistribution.pdf. I hope you downloaded that before you began this presentation, and I hope that you're able to refer to it multiple times as we proceed with the rest. Before we go on, though, I need to orient you to the way this table works. There are 4 columns in the table. They're labeled A, B, C, and D. Column A is the z-score itself. Wherever in your distribution you have marked your z, that is what's referred to in column A of the table. The z-score might be, as we've said before, +1, +2, or it could be +0.02 or +0.27, or any value. But wherever you mark your z, that's what's articulated in this column. Column B says the proportion in the body. That means from the z-score into the bulk of the rest of the distribution, that is the proportion of scores that fall in that shaded region. So B corresponds with the big bulk body of the distribution. In other words, if, for instance, your z were 0.33, then your B body would be 62.93% of scores falling in that section of the distribution. The column C, one moment. Always, this represents the larger portion of your distribution, no matter which side your z is on. Please remember that if your z is over here, the body would be in the bulk, the big, bulky part of the distribution over here. So it doesn't matter whether it's on the left or the right side. What matters is whether it's the big portion or, as we see in column C, the small portion in the tail. So this is the same Z as we articulated up at the top, but instead of being the big, bulky body portion, this is the proportion in the tail. So if you look at, again, the Z of 0.33, you see that 63% of the scores are in the body, but the reciprocal of that, the other remaining scores, 37%, are in the tail. And those two sections together add to 100%, because all the scores have to be either below or above that Z-score. Finally, column D represents the proportion between the mean and the Z that you've chosen. That represents, as you can see here, between the Z and the mean, this shaded portion. This will come in handy in a couple of examples that you'll see later on. Let's use it for a couple of examples. What if we wanted to know the probability of selecting someone by chance with an SAT score that was less than 525? The first thing we'd have to do is transform that into a Z-score. X minus the mean divided by standard deviation, that's 525 minus 500 divided by 100. That gives us a Z-score of 0.25. Once you have the Z-score, then you can find the Z-score in the table. So you look for 0.25 in the Z column. Here we find 0.25. Then we have to ask the question, what is the proportion in the body? Because we're asking the question, what is the probability of selecting someone by chance with an SAT score less than 525? So this is the point at which the Z-score falls. This is the proportion of the curve that is less than that Z-score. And this is the body because it's the bulkier, bigger part of the distribution. So we could go over to the table, find 0.25, and the proportion in the body, column B, proportion in the body, is 0.5987. 59% of the scores fall below 0.25. So 59% is the likelihood of getting somebody less than an SAT score of 525. What if we wanted to know instead the probability of selecting someone by chance with an SAT score greater than 525? That would just be to say, instead of knowing the shaded portion in the body, what if we wanted to know what was the portion here in the tail that was greater than 525? Go back to your table, the same Z-score, 0.25, but this time use column C where it says the proportion in the tail. And note here that the proportion is 40%, 0.4013, and that we could then say is the probability of drawing a score at random greater than 525. What if we wanted to know the probability of selecting someone by chance with an SAT score greater than 475? The first thing we would have to do, again, is to transform that score into a Z-score. 475 minus 500 divided by the standard deviation of 100 is negative 0.25. So you go and find that Z-score in the table. But there are no negative Z-scores listed in the table. That's okay. You just look up the positive Z-score, and the proportions in the body and tail are still accurately represented by the table values. So even if you're looking for a Z-score of negative 0.25, come over to see the Z-score that's positive 0.25, and you'll see that the correct portion in the body and the tail are still listed. So here, the proportion in the body is just reversed of what it was in the last problem. It's 59% here, and it's 40% here. Let's practice with a couple more. Please get out your normal unit distribution and look at the table to figure out the answers to these questions. What proportion of the normal distribution corresponds to Z-score values greater than 1? Pause your video if you need to. Look at the table. you should find that in your table, a z-score of 1 is listed at the top of the column. And the proportion in the tail is what we're looking for, because we're looking for scores greater than 1. Here, the proportion in the tail is listed in the table as 0.1587. So, the proportion that is, that's your answer. That's the proportion of scores above 1. For a normal distribution, what's the probability of selecting a z-score less than z of 1.5? Please pause your video. You should find that, again, the z for 1.5 is listed at the top of a column in your table. That 1.5 has an associated proportion in the body of 0.9332, because that right there is the big, bulky body portion of the distribution. 9.9332, 93% of the scores are below a z of 1.5. What proportion of the normal distribution is contained in the tail beyond z of negative 0.5? Please pause your video, work through that. You should remember that a negative z-score is not listed in the table. So you look for the positive z-score, 0.5. You see it here. And then you look for the proportion listed in the tail, because we're looking for things lower than or beyond in the tail, lower than negative 0.5. The proportion in the tail is 31% or so, and so the answer is 0.3085. Now, if you know the z-score, you can look up the corresponding proportion and probability, as we've been doing. But if you know the proportion or probability, you can also use the table in reverse to find a specific z-score that matches it. Here's an example. For a normal distribution, what z-score separates the top 10% from the remainder of the distribution? If I sketch it out, it looks like this. We're looking for the z-score here, which we don't know, that corresponds with the value that separates the top 10% from the bottom 90%. You should pause the video for a second and look if you can see that in your table. Note that you won't find exactly 0.1000, which corresponds to this top 10% in your table, but you can find the value that's closest to it and use that instead. As you see, the value that's in the tail corresponding with 0.1000 falls right here. This is the closest value to it, and so we find a z, working back through the columns of the table, of 1.28. So the answer is a z of 1.28 separates the top 10% from the bottom 90%. For a normal distribution, what z-score values form the boundaries that separate the middle 60% of the distribution from the rest of the scores? I've sketched this once more, and you can see that what I'm asking is for, given the bulk of your distribution, what is the middle 60% bounded by? A z-score here and a z-score here. How would you go about answering this question? It might be difficult until I draw this line here. Does the answer become clear? This half of the middle 60% is 30%. Now we can suddenly use column D in the table. This is the proportion between the mean and z. So if we're looking for between the mean and z, what is the z-score that corresponds with 30% in this region? If you come over, you can see that 30% is closest here to 0.84. And so the positive z-score here would be positive 0.84. And on the negative side, remember, we're just reversing that. So we would just make a negative 0.84 because the 30% here is reflected in the table as well in column D. And negative z-scores aren't listed in the table, but you just have to know that negative 0.84 is the reciprocal of this positive 0.84. Now I want to make a note really quick here on sketching. You probably noticed that in each of the problems that we went through before, we sketched a distribution. As a general rule, you should always sketch a distribution. You should locate the mean with a vertical line and shade in the portion that you're trying to determine. Remember, look at the sketch. It will help you determine which of the columns you're supposed to be using in the unit normal table. If you make a habit of drawing sketches, you're going to avoid careless errors when you're using the table. I've had plenty of very bright students make careless errors by not drawing the distribution. So I strongly recommend always draw what your problem is. I also have a note here on probability. The probabilities given in the unit normal table will be accurate only for normally distributed scores. So the shape of the distribution should be verified before you use it. Now, in this class, because you don't have the ability to verify the samples that we're giving you, or because you don't have the patience to run very sophisticated statistics on very large samples by hand, we're going to just tell you that in any given situation, the distribution is normally shaped. So you can trust the table, use the table, get used to the table. But in real life, when you're running real statistics, you have to verify that the shape of the distribution you're drawing this from actually is normal. In more sophisticated and advanced statistics classes, you'll learn more about that. Our previous examples involved looking up the z-scores and finding the proportion of a distribution that was either above or below that score. However, you often need to find the probabilities associated with a specific x value. For example, it's known that IQ scores form a normal distribution with a mean of 100 and a standard deviation of 15. You might recall that I explained that in the previous module, where it doesn't naturally happen that way, but we go through a process of standardizing things so that we force the distribution to have a mean of 100 and a standard deviation of 15. Given this information, what is the probability of randomly selecting an individual with an IQ score that is less than 120? In order to solve this problem, you'd first need to transform the x score into a z-score, and then look up the proportions that correspond to that z-score. So, if you have a distribution of IQ scores with a mean of 100 and a standard deviation of 15, you might be asking, what percentage of people have scores lower than 120? But in order to do that, we have to figure out what is the z-score that corresponds with that 120. If you compute it, remember x minus the mean divided by the standard deviation, you get a z of 1.33. The next step is to look up the z-score value in the unit normal table. You should find, if you go to the table and look it up, that the value is 0.9082. As previously mentioned, we can phrase these questions in terms of probability or proportion, and the outcomes are equivalent. We can also phrase them in terms of percentile ranks. Percentile rank is the percentage of individuals in the distribution who have scores that are less than or equal to the specific score you're interested in. You've no doubt encountered these before. You might say, when I took the SAT, I was in the 64th percentile. That means 64% of people scored as well or less than you. Here's an example of computing the percentile rank. Let's say that you earned 700 on the SAT. Remember that SAT scores have a mean of 500 and a standard deviation of 100, as I've shown here on this graph. In what percentile did you score? What you're asking here is, what is the percentage of scores that fall underneath your score of 700? The first thing you have to do is compute your z-score, which of course is x minus the mean divided by the standard deviation, or 2. So your z-score corresponds with your original score corresponds with a z of 2. And then you can go to the table and you can figure out what is the proportion in the body that corresponds with a z of 2. And that's 97.72 Or you could say that you're in about the 98th percentile. You can also use the principles that we've discussed so far to find the proportion that's located between two scores. For example, the Highway Department conducted a study measuring driving speeds on a local section of interstate highway. They found an average speed of 58 miles per hour, that's shown here on the graph, with a standard deviation of 10 miles per hour. The distribution was approximately normal. Given this information, what proportion of the cars are traveling between 55 and 65 miles per hour? You would expect them to fall something like this, given that the speed limit on the freeway is 60 miles an hour. Well, I guess it's not everywhere. It's not outside of Ellensburg, but in a lot of places it's 60 miles an hour, and in this area it was 60 miles an hour. And so some people go about 5 over, some people about 5 under, but the distribution that we're interested in is between that 5 over and 5 under, even though most people go a tiny bit under. On average, we find that people go a tiny bit under the speed limit of 60. So we want to know what percentage of people go between 5 under and 5 over the speed limit. How could we do that? Well, first we'd have to figure out what are the z-scores that correspond with a speed limit of 50, with a speed of 55 and a speed of 65. X minus the mean divided by the standard deviation will yield for us a z-score of negative 0.3 and positive 0.7. I've put those here on a second distribution x-axis, and you can then ask the question, using column D of the unit normal table, what are the proportions that correspond with negative 0.3 and positive 0.7? If you go to the table, you should see that negative 0.3 is associated with 0.1179, positive 0.7 is associated with 0.2580, and those are correspond with this section and this section. You can add those two together, and that tells you that 37.59% of people are traveling between 5 under and 5 over the speed limit. Using the same distribution and the same driving speeds that we used in the last example, we might also ask what proportion of cars are traveling between 65 and 75 miles per hour. Well, here we have to again find the z-scores that correspond with 65 and 75. Remember, x minus the mean divided by the standard deviation, that'll yield for us 0.7 and 1.7. Now, how do we use these z-scores in the table, the unit normal table, to get the proportions that we're interested in? You could look at the proportion in the tail beyond 0.7. That's this entire region here, all of this region. But, problematically, this section here is not a portion that we're actually interested in. So if you look at this entire region, you'll find that the probability is 0.2420, or 24% of scores falling in this region. This proportion includes the section we want, but it also includes that unwanted part but beyond the z-score of 1.7. So we have to also find the proportion in the tail beyond 1.7 using the unit normal table, and you'll see that in column C in the table, the probability is 0.0446. If you take the total portion beyond this point and subtract from it the portion that's here in white, you'll notice that there are 0.1974 scores falling in the shaded region here. In other words, about 20% of people drive between 65 and 75 miles an hour on a on a freeway where the speed limit is 60 miles an hour. So far, what we've done is, using x-scores, we've computed z-scores and then found the proportions or probabilities that correspond with them in the table. But we can also reverse that process and start here with the proportions or probabilities, find the z-scores that match, and then compute an original score. Here's an example of doing that. Let's imagine that Americans spend an average of 24.3 minutes commuting to work each day. Does that match with how long you commute? I commute way, actually now, I just recently moved. I was commuting for several years for about an hour and 45 minutes each way. It was abysmal. But recently I've changed homes, and I've got about a 15-minute commute in the car, but then of course the parking lot's kind of far from my actual office, so it's about another 10 minutes of walking. So I am almost exactly at this average. When I was teaching full-time in Ellensburg at the Central Washington University campus, I had a 7-minute drive and about a 3-minute walk into the building, and so I was far lower than the average of 24.3. But you might think to yourself, where do you fall in this distribution? Assuming that the distribution of commuting times is normal, with a standard deviation of 10 minutes, how much time do you have to spend commuting each day to be in the highest 10% nationwide? Now, I'll guarantee you, without even running the stats, that my old commute of an hour and 45 minutes was in the top 10%. That's very, very long of a commute. But we want to know, what is the boundary? What is the score here? The number of minutes that defines the top 10%, the highest 10% of commuters. Well, the first step that we have to do is figure out what is the proportion, the z-score, that matches the proportion of 10%. If you look at the proportion in the tail column, the one that's closest to 10% is 1.28. So we'll mark that as our z, 1.28. Now, using the formula that we saw in the last module, x equals the mean plus z's times the standard deviation, we can plug in our values of the mean 24.3, the z of 1.28, which we just obtained, and the standard deviation of 10. If we carry that formula through, we get 37.1 as the score that corresponds with the z of 1.28. That is the number of minutes that somebody has to drive in order to be in the top 10%. Where do you fall? Are you in the highest 10% or are you in the lowest 90%? Using the same distribution, what range of values defines the middle 90% of the distribution? There are 5% in the upper tail and 5% in the lower tail, but we want to know, what is the proportion in the middle 90%? What is the number of minutes that surrounds the lowest and the highest values of the bulk of the middle bunch of people, most people? In order to find that, we first have to go to the table and we have to figure out what is either the z-score that is associated with 5% in a tail or with 45% in column D. So if we go here to the table, you'll see that those are the same z-score. If you find 5% in the tail, that's about right here. Or you can find 45% in column D, which is between the z and the mean. But both of those are on the same line. They give you the same z-score of 1.65 right there. So positive 1.65 on the upper end, negative 1.65 on the lower end. Both of these z-scores have to be used in your formula, x equals the mean plus z times the standard deviation, in order to give you the lower bound and the upper bound. So you might take that formula, plug in the mean and standard deviation with the positive z-score and the negative z-score, and discover that the two numbers of minutes of commuting that bind the middle 90% are about 8 minutes to 41 minutes. That's where the middle 90% of commuters are traveling for. Now, as we wrap up the rest of this chapter, I want us to still be looking ahead to inferential statistics. When we get a couple modules in the future, we're going to start running our inferential statistics. But everything we've learned so far is just foundational, just helping us to understand the principles associated with these inferential statistics. Many research situations begin with a population that forms a normal distribution. In this little schematic here, you can see that the population is defined as normal with a mean of 400 and a standard deviation of 20. you might then draw a random sample from that population, give it a treatment, and then see if the treated sample is noticeably different from the population. If it's noticeably different, that means our treatment did something. It either made them higher or lower, it made them better or worse. It did something if they're different from the population. But what qualifies as noticeably different from the mean of the population at 400? What if you treated your sample and it was 415? What if the mean of the sample was 420 or 450? We need some kind of standardized measure to define what is extreme or what is noticeably different, so that when we look at the sample, we can say reliably, this is different from the population. Or, in other words, our treatment actually did something. So if we were to take that distribution of scores that had a mean of 400 and a standard deviation of 20, we might say the middle 95% of the scores are reasonable, average, typical, normal scores. Those scores that fall in the tail on either side are extreme scores. They're the extreme 5%. They're scores that are very unlikely to be obtained from the original population just by chance, and therefore they suggest that our treatment actually worked. This tail right here corresponds with 2.5%, and this tail corresponds with the other 2.5%, because added together, these two tails have to come to 5%. So that 5% is split between the upper and the lower two tails. And the middle 95% is the rest of the scores. So if we add boundaries that separate out the middle 95%, a z-score here and a z-score here, this can provide an objective criteria that all scientists use universally for making a decision that says our treatment worked or it didn't work. And those z-scores are about -2 and +2. They're not exactly, because remember at the beginning of this module I showed you that the middle 95% is not quite negative and +2. If you look in your unit normal table, you'll see that it's actually at -1.96 and +1.96. Because if you used the z-scores of 2, then the middle 95% wouldn't actually be 95. It's like 95.44 or something like that. And so in order to get exactly 95% in the middle, we use this z-score that's almost -2 and this one that's almost +2, but not exactly, not quite. If the sample mean that we treated, that we gave some treatment to, we drew from the population, we treated, and we compute the sample mean after treatment, and its mean falls beyond the positive or negative 1.96 boundaries, it falls either here or here, then it's extremely unlikely that that sample was drawn from the population and happened to have a score that big just by chance. Like, as in, the treatment really had no effect, but we just happened to draw that score. It might be the case, but it's unlikely to be the case. So, when you come to a statistic in a scientific paper, you will often see something written like this. It might say like t parentheses 10 equals 4.5, comma, p equals 0.01. This p right here deals with exactly what we've been doing the entire module up till now. This p is saying the probability of drawing a score like this just by chance. Scientists don't write out what the event is in parentheses after this p because we already all know it. It's just standard scientific jargon. And what is that p? It represents the probability of finding results this extreme, whatever that statistic is. We found a mean of some extreme value, or even more extreme, if we were wrong about our hypothesis. Now I know that's a little bit of confusing verbiage here, so I'm going to go back to the example that we used at the beginning of the module. If you drew a sample of 4 black marbles from one of these 2 jars and you didn't know which one it was, you would guess that it came from the second jar, because it best matches that jar. But there is some chance that you're wrong, and it actually came from the first jar. And the probability that we're listing here in our scientific papers is the probability that we're wrong. Basically, the probability of finding really extreme samples like this. that look like they're from this population, but they're actually not. Or, you might say alternatively, when thinking about our treated samples, if we drew a sample of 30 people and we gave them some treatment and they had a really high mean and it seemed like it worked, maybe the treatment actually didn't work and we just happened, by dumb luck, to grab a bunch of people who scored high on whatever measure we're interested in. And really, that population came from, or that sample came from a population where a treatment doesn't work, but it looked like it worked. And so we compute the probability that we're actually wrong. And if it's a very low probability, like less than 0.05 or 0.01, then we can say, okay, this probability is so low that we're confident our treatment probably worked. There's always a chance that it didn't actually work, and that it's the 1% of times when we were wrong. But we feel confident enough when we publish a paper saying that this is very unlikely to have occurred just by chance. It's probably that the treatment actually worked. We don't know for sure, but we think we're pretty confident that this treatment actually worked because the probability that we're wrong is so low. Now here at the end of the module, I'd like you to work through one last practice exercise. Imagine you're a professor at a university. You look at data compiled by the administration, and you note that at the end of the term, the average grades of each course is normally distributed with a mean of 80.3%, with standard deviation of 3.2. So that's the typical score of the average of each class grade. So Psych 101 and Chemistry 480 and Physics 230 and Art 180 or whatever. If you look at the percentage of scores that people are earning in the classes, the average among them is 80%. But sometimes it's a little higher, sometimes it's a little lower. The first thing I want you to do is sketch the distribution with that mean and standard deviation. And then sketch what the distribution would look like if every score were transformed into a z-score. You want to know if you are an especially difficult professor. You define especially difficult as being in the hardest 10% of classes. So, find the z-score that separates the lowest 10% of course grades from the rest. Plot on the z-distribution that you made for part 2 above, this part right here. At the end of the term, you calculate the average grade that your class earned, and you find that it's 75.1%. Transform that score into a z-score and then plot it on that distribution. Did your class fall in the lowest 10% at the university? Are you one of the toughest teachers? Please pause your video before you go on. I'll show you the answer in a moment. Hopefully you worked through and saw that the first thing you would need to do is draw a distribution with a mean of 80.3 and a standard deviation of 3.2. If you changed this entire distribution into z-scores, it would have a mean of 0 and a standard deviation of 1, as all z-transform distributions do. The next thing you need to do is draw a z-score that separates the bottom 10% from the remainder of the distribution, because you want to know if your class is in the lowest 10% scoring, if your students are doing much worse than all the other students. Then you go to the unit normal table and you find the z-score that corresponds with this lowest 10%. The proportion in the tail corresponding closest to 10% is a z of 1.28. That 1.28 is listed here on the negative side of the distribution because the z is below the mean. And what you next need to do is figure out that your mean is 75.1 in your class. The z-score corresponding with your mean is negative 1.625. And that, plotted in the z distribution down here, falls about there. It's in the tail of the distribution, in the hardest 10%, suggesting that you might be one of the toughest teachers at Central Washington University.